In previous lessons, we've talked about integration by substitution and reversing the chain rule, and that was theoretical, and now I want to use some very practical examples. And I think the biggest obstacle to becoming facile with using integration by substitution is being able to recognize forms. So let's look at an example then very quickly. We're looking for the form, the integral of a composition times the derivative of the inner function dx. Because remember we said that the integral of f prime of g of x, g prime x dx is equal to f of g of x plus a constant. So if we have this integral form, it gives us an easy way to calculate what the value of that integral is. It's f of g of x plus c. But all of that said, we have to recognize a composition. And the form would be the composition of functions times the derivative of the interior function, or the inner function. So maybe all of that's a little too abstract. So let's try to look at an example. Let's look at 1 plus x squared. Now if that was a function that was given to you, would you see that immediately as a composition? And most of us probably would say no. But let's break it down a little bit. Let's suppose that we would look at a g of x function as being 1 plus x squared and an f of x function as being 1 upon x. Now what does this functional notation mean? It means that g takes its independent variable, squares it, and adds 1. Now what does f do to its independent variable? It just takes the reciprocal. Okay, then what if we look at f of g of x? Well, that would be f acting upon g, so that would be f acting upon, what does g do? 1 plus x squared is the result of g acting. Now let f act upon that argument, and it takes the reciprocal, 1 plus x squared. So in fact, this can be seen as a composition of functions, which maybe explains the steps we go through if we're going to try to integrate 1 upon 1 plus x squared 2x dx. We need procedurally to look for a composition. Let's get a bright color here. We need to look for a composition, and from what we've just seen here, we've found our composition. So we've got a composition. Now is this in fact the derivative of the inside function? And if this is f of g of x, here's your inside function, 1 plus x squared. And the derivative of 1 plus x squared dx is equal to 2x. So we've got the form we need. It's the composition of functions f prime of g of x. We don't know what f prime is, but we see it's f prime acting upon g of x and then the derivative of g of x. So here's the technique of substitution. We want to let u equal that inner function. And in this case, that's 1 plus x squared. Then if u is that inner function, 1 plus x squared, du would be, and here I want the differential, so that's going to be 2x dx. Now look back to the function that we're integrating. This is the, let's just call it I. Say I for integral is equal to, then I is equal to the integral of 1 upon, well, that's 1 upon u, isn't it? Just substitution. And what's left is a 2x dx, but 2x dx is du, so it's 1 upon u du, and so simple. The integral of 1 upon u du, it's one of the 5 things we need to know, would be natural log absolute value of u plus a constant. And then the final step would be to go from the u variable back to the original variable. U is 1 plus x squared. So this then is further equal to the natural log of 1 plus x squared plus a constant. So, first example. Now with a clean slate, let's look at another example. This example is x cubed plus the log of x to the 5th power, and then times the factor 3x squared plus 1 upon x, and we want the indefinite integral of this expression dx. That is, we want to find a function whose derivative is equal to this whole expression right here. That looks pretty daunting, but maybe it's not that hard. When I see a function like this, an expression like parentheses, something to a power, I know I can see that as a composition of functions. So here's my composition. I'll just abbreviate that as COMP. Now that's a composition of functions. The outer function would be raising to the 5th power. The inner function would be x cubed plus log x. Now the question is this the derivative of the inner function? Is that the derivative of the inner function? Well, if the inner function is x cubed plus log x, the derivative would be 3x squared, yeah, plus 1 upon x, yes. All right, so this is the form f prime g of x is the inner function, times g prime of x. So the easy way to calculate the value of this indefinite integral is to let u be the inner function. U will be x cubed plus natural log x. Then what can you tell me about du? Du, the differential, would be 3x squared plus, and what's the derivative of 1 upon x? Natural log x, and then all dx. And like that. So du is 3x squared plus log x dx. Well then, what does my integral look like? Again, if I'll use the abbreviation here, I is the indefinite integral, then I is equal to, well, this looks like u, doesn't it? That's just u, compare, and this is 3x squared plus 1 upon x dx. That's just du. So using substitution, I can rewrite this integral as u to the 5th power, and then what I have here, all of this, is just du. And that's an integral that it's easy to evaluate. This is going to be u, increase the exponent by 1, divide by the new exponent, plus a constant. But we're not quite done, because this is the value in terms of u, but I really would want the value in terms of x, but that's just an inverse substitution. So this is then equal to x cubed plus the natural log of x divided by 6, and all of that numerator to the 6th power, and plus an arbitrary constant. So there we have a final version of I. So this integral, when you broke it down and used substitution, was really not hard at all to evaluate. Now let's try another example. Let's look at the integral of, say, 4x squared times the square root of x cubed plus 5 dx. And maybe we should change colors. So let's go with green. It's kind of a nice color here. So new problem. All right, what do we have? Well, it looks like the square root, that's kind of a parentheses with an exponent, isn't it? A fractional exponent. This can be looked at as a composition of functions, and so if this is my composition, then the question is what remains the derivative of the inner function. The inner function would be x cubed plus 5, and the derivative would be 3x squared. And when I look over here, well, I don't have a 3x squared. I've got a 4x squared, so it doesn't quite fit the form. But we know how to fix that. Thinking about the 5 things that you must know, I know how to fix that. First of all, here's the fix. I can take the 4, this 4 right here, I can take outside the integral. Now also, I can multiply the integral by 1. Multiplying by 1 doesn't change the value since 1's an identity for multiplication. But this is going to be in the form 1/3 times 3, so there's my 1, times the integral of, I took the 4 out already, so I've just got an x squared root x cubed plus 5 dx. And scroll up just a tad. And then what do we have? Well, here I can take this 3. Let me change colors again. I can take this 3 right here and I can migrate it inside because we know that constants will move in and out of the integral. So making that change, I would say is equal to 4/3 integral 3x squared square root of x cubed plus 5 dx. With more practice, we'll be combining steps, but what I want to do for illustration right here is to take this 3x term and I want to move it over here with the dx, and so I would finally say this is equal to 4/3 integral square root x cubed plus 5 and then a 3x squared dx. Alright, why is that? Because this looks like a composition of functions with x cubed plus 5 being the inner function. The derivative of x cubed plus 5 would be 3x squared. So here's the derivative of the inner function. And now I know I can use the technique of substitution. And to do that, I'd let u be the inner function, which would be x cubed plus 5. Then du would be 3x squared, derivative of 5 is 0, and a dx on the end, so that the integral that I started with, I, is equal to the integral. Now here it is. Let's look at it. Let's look at it in this form right here. Would be the form to look at it. Would be 4/3, just a constant out front, but inside I see the square root of u, and then 3x squared dx, well, that's just du, which is equal to, and as I said, when we gain more experience, we'll be skipping some of these steps, but this is u to the 1/2 du. And we can use our rules for power functions and see that this is going to be 4/3, and it's a power function, so it's u. I have to increase this by 1, so the exponent becomes 3/2, and divide by the new exponent, so I'm dividing by 3/2, plus a constant, and now we got a little algebra to do here with these exponents. Dividing by 3/2 is the same as multiplying by 2/3, so I'm going to try to clean this up a little bit. That's the 4/3. Instead of dividing by 3/2, we're going to multiply by 2/3. And then instead of u, well, u is really just a substitution for x cubed plus 5. So I'm going to put an x cubed plus 5 in here, and that's to what? That's to the 3/2 power, and it's plus a constant. And the final thing I'll do, this makes the form better, but it doesn't really change the numbers. Instead of 4/3 times 2/3, I could say that's 8/9. So this is an 8/9 times x cubed plus 5 to the power 3/2 plus a constant c. And that would be the That would be the results. That's the answer. Antiderivative of this expression that we started with is this expression that we ended with. And can you check that? Well, sure, you can check it. Take a derivative of this and see if you get this. But I know you can do that, so I'm not going to do that with you right now. You ask me if you have any trouble doing that. Thank you.